So linear reservoir is characterized as storage is directly proportional to discharge. That means if you are increasing discharge, storage will change directly. And also there is attenuation. Attenuation means the change in value of peak. Because in case of reservoir routing, what happens? Flood wave is coming from a channel to the reservoir. So suddenly the width of the water carrying infrastructure changes. So that is why it has a big volume of water coming inside at a time. And so the peak is raised and raised more than what the original peak was. So this is the difference between these two peak values that is being referred to as attenuation. And so for linear reservoir, assume that storage is directly proportional to discharge and attenuation is there. Now here comes the linear channel. In case of linear channel, there is no attenuation. So no attenuation assumed. And in case of this one, this time, so what we have now is that we have also derived the Muskingum equation. X is equal to K within bracket, fourth bracket, xi plus 1 minus x q. Actually, that I to the power m or q to the power m, that m is replaced by 1. That is a normal, in case of normal catchment, m is 1. And x is your weighting factor that you will decide how much you will give. And k is storage time constant having an unit of time. Okay, so he is basically the timekeeper. So what it is done, to put the value of k, value of x, and value of I, and value of q to get SA. Okay, so this is the theoretical discussion that we have created, and the next is routing in conceptual hydrograph development. So for this only you are assuming that all the reservoirs are linear and all the channels are linear. If they are linear, then storage will be directly proportional to discharge. There will be attenuation in case of linear reservoir, and in case of linear channel there is no stability. Let me say that there is a linear channel, and yes, there is no attenuation, only translation. That means time required for a flood wave to translate in a reach is assumed to be constant. So the time is also made constant. Not only m, the time is also made constant, and on time the k variable depends. Okay. So in addition to this, there are two more classes or categories. One is Clark's method of UG. One is Clark's method of IE, which is instantaneous unit hydrograph, and Nash conceptual model. So these two, and another thing, how the routing is done with the help of Muskingum method. These three I will take in the next holidays. So let us see what happened. So for now, this is the case. Thank you for your patient hearing and activity. So until now we have understood that routing can be divided, flood routing can be divided into reservoir routing or storage routing and channel routing. Now channel routing can further be divided into hydrologic routing and hydraulic routing. And channel routing is, always remember, channel storage is a function of both inflow and outflow, not only outflow. Okay, and for reservoir routing, it is storage is completely depends on the outflow. So channel routing is dependent on inflow and outflow, and storage routing is dependent on outflow only. Now this channel hydrologic routing can be further divided into prism and wedge routing. So what is prism? If you imagine a parallel surface, if you imagine a surface parallel to the bottom of the river, then anything below this parallel surface or parallel water surface level is known as prism storage, and anything above the this imaginary line is your wedge storage. However, if the real water surface profile is above this imaginary surface profile, then it is known as positive wedge, and if this real water surface profile is below the imaginary water surface profile, then it is known as wedge storage negative or negative wedge storage. So this picture is clearly shows what we want to mean, right? So this continuous line is the real water surface, and this dot 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 line or line with gaps is the imaginary plane, and between these two planes whatever is there is known as wedge storage. Positive if real water surface is above the imaginary plane, negative if it is below the imaginary plane. So that is the history of this prism storage and this wedge storage. Now this hydraulic routing can also be further divided into approximate method and complete numerical method, but the main thing is that you have to solve the Saint-Venant equation. So when you are converting Saint-Venant equation into algebraic equation and solving it, then it is known as direct method. Now if all the variables depends upon the independent variable, which is time or space, and both of them both input and output belongs to the same time or same space, then it is implicit. If any one of them are out of time domain or out of space domain, then the equation is known as explicit. So overall it is clubbed under the direct method. Now method of characteristic is there. This is also a complete numerical method. So method of characteristic here also you have to solve the Saint-Venant equation by dividing it into multiple nodes or multiple grids. Okay, and then it's solving it. So here nothing but Saint-Venant equation is converted to multiple ordinary differential equations, and they are solved as per rule. Now there are finite element method also. So for finite element method, directly introduce finite element method. Okay, so this is what is complete numerical method hydrolytic routing, and approximate method has three subcategories also. One is continuity equation, another is drastically curtained equation, and someone else. So this is what your hydrologic routing is. What is your channel routing is, not I will say hydrologic routing. Now comes to your question of what is the Muskingum method and its equation. So what I will is the storage in the channel depends on both inflow and outflow. So we have devised the equation like this. AC is equals to K within bracket x into I to the power m plus 1 minus x into q to the power m, where m is a constant exponent and x is a imaginary variable or imaginary coefficient, and so is the k. Now k depends mainly on the time of concentration or traveling time of the flood wave, and x is basically the weighting factor. That means it give weight to inflow and outflow. That means how much weight you are giving to your inflow value and how much weight you are giving to your outflow value. So by the equation you can say they are giving greater weightage to inflow than to outflow, because in case of channel routing they are mainly controlled by the inflow. Okay, there are not much effect for outflow. That is why Prism Storage is, although the Prism Storage is a function of this channel routing only, that is queue only, whereas this one is not affected. So this I is inflow. So in case of channel routing, what happens? Inflow is taking part, but not as much part as the outflow is. So that is why this x or weighing factor is Im, and 1 minus x, that is the remaining weightage is q. Although from x and 1 minus x you cannot understand which one you are giving higher weightage, right? So this is the overall equation, is equals to k into x I to the power m plus 1 minus x q to the power m. So if we assume that m is equal to 1, which is the case in the real life, all the watershed have m equals to 1, and x I have already discussed, it is a weighting factor. So k is storage time constant having a unit of time. So all these things, what I want is that you understand what storage is in a channel routing. Storage in channel routing is some amount of water is coming from upstream inflow, some of the water is going out at the same time from downstream. So this difference of this time and the volume will give you the storage. Okay, and this one, if we assume m to be 1 and x is the weighting factor, then s become k into xi plus 1 minus x. So if m is equal to 0, m is equal to 1, then that same equation here, the same equation here, okay, so this one without m or without exponential coefficient, what I would say, constant exponent, and without this constant exponent, the equation becomes S storage equals to K, storage time constant, into X into I plus 1 minus X into Q. So this is the case, and this equation is known as Muskingum equation. S equals to K xi plus 1 minus x multiplied by q. So actually they have reduced the weightage of discharge in this process. Okay. Now the next concept is how to develop conceptual hydrological models. Okay, so there are two types of reservoir, and let's start just debriefing you. One is linear reservoir, another is reservoir linear channel. So one is this one, linear reservoir, another one is linear channel. And so in case of linear reservoir, the assumption is storage is directly proportional to discharge, just like hydrological routing. And there are attenuation. Remember, in case of reservoir routing, attenuation is common because the water is coming from a channel to a reservoir. So its width of the river changes. Its peak will be below the imaginary water surface profile. Okay, so that is why at that time in the downstream it is known as negative prism storage. So H subscript P indicates the prism storage. Now here is another catch. In case of prism storage, you see with distance, if the depth is same, I have said that prism storage is assumed to be uniform. So from where this storage can be diminished or used, the water stored in Prism, how can we use it? Only through the outflow. Because as there is no incoming of water, the depth of the this water surface level is not changing. That is what we have assumed. So that is why if we want to change that depth, we have to open the outlet so that water can goes away, flows away through the outlet only. So that is why. And also, if you imagine it realistically, water will always go from up to down. So the storage will change only if our downstream is clear. So that is why Prism storage is always a function of Q, the outflow. However, the wedge storage is a function of inflow. You know why? Because from inflow, this flood water is coming and it is increasing the real water surface level. So it is increasing the wedge storage also. And when it is going down, that means the water has gone out from the channel, and as a result the wedge has become negative. So wedge storage depends only on inflow of water, whereas the Prism storage depends only on the outflow of water. Okay, so just take an example. If you block a channel in the downstream and you have opened, or you have kept the inflow to be continuous, that means inflow is coming continuously, then what will happen? Wedge storage will increase because it is being not allowed to go outside through the downstream. So it will only increase the storage, right? So inflow is coming, wedge storage is increasing, but not Prism storage. Because for Prism storage, we have assumed that with distance the depth is uniform. So anything below parallel surface, anything below the imaginary water surface profile is the Prism storage, and that storage do not change with distance as the depth is uniform. It can only change if your outflow is cleared. There is no outflow. So that is what is Prism storage and wedge storage is, and both are under channel routing, and from channel routing, hydrologic routing. So channel routing is further divided into hydrologic and hydraulic routing. In the hydrologic routing, there are Prism routing or Prism storage and wedge storage. Prism storage is the water stored under the imaginary water surface profile, which is parallel to the channel bottom, but it is imaginary, and anything above that imaginary surface profile, it constitutes the wedge storage. So basically, wedge storage can be positive if it is above the imaginary water surface profile, and can be negative if it is below the water surface profile. But there is no such case in Prism storage, because for Prism storage we have assumed that the depth will be uniform throughout the channel. So, okay, now for hydraulic channel routing, there are three different types of channel routing you can observe. So what are they? So they are known as, one is approximate method, another one is complete numerical methods. Look, hydraulic routing, in case of hydraulic routing, we try to solve the Saint-Venant equation. So what is Saint-Venant equation? You can search in the internet. It is a simple partial differential equation which we try to solve for the given boundary and initial and boundary conditions. So in case of approximate methods, there are three different types of method. One is solve the continuity equation. Second is solve the drastically curtailed equation of motion. Third is other methods similar to the hydrologic storage routing. So about hydrologic storage routing, there are level pool routing, there are Goodrick routing, there are standard fourth order range Kutta, Runge Kutta routing, and so it is known as standard fourth order Runge Kutta method. Okay, and there is also modified pulse method. So this is the three main most popular methods of hydrologic routing. So there is that method in case of that method. So those methods are also clubbed under the approximate methods. And yes, of course, you can solve continuity equation or solve the drastically curtailed equation of motion. So these are all approximate method. These are not exact method. So in case of complete numerical methods, there are three different methods. One is direct method. Another one is method of characteristics. Another one is finite element methods. And in case of direct method, you can further subdivide it to implicit method and explicit method. So all these direct method is nothing but they are some partial differential equation or PDE converted to algebraic equation by FDM, financial differential method. And then there are specific discretization rule with which those equations are being solved. Okay, so if you are solving in the same domain, that means the variable you are predicting and the input with the help of which you are predicting the output is in the same domain, time domain or space domain, then it is implicit. If one of them are out of that domain, then it becomes explicit. Okay. Now, direct method is one, method of characteristic is another. This method of characteristic can be further subdivided into characteristic nodes and rectangular grids. Now here also the simple Sen-Venant equation, which is actually a partial differential equation, is converted to ordinary differential equation, and then it is again same discretized and solved by the discretization methods. And lastly, this is the finite element method that we already knows about, and I will share a link about this sorry by description of this video. So now let us see. So we have that hydraulic routing, we know what it is. So here I am also saying hydraulic routing is nothing but solution to the basic Sen-Venant equation. Now how we were solving it, based on that you can categorize it into approximate method and this complete numerical methods. In case of complete numerical methods, the direct and method of characteristic is solved by the FDM, and remaining are finite element method. And direct method can be implicit, can be explicit, based on the position of the variables in the time or space domain. And method of characteristic is further categorized into characteristic nodes or grids. That means you can either solve it by discretizing into nodes, or you can solve it by discretizing into grids. So both way it is allowed, and it is nothing but SV, Sen-Venant equation is converted to ODE, ordinary differential equation. So this is what the lecture is. Now let us see, to solve the hydraulic routing, flood routing, under the complete numerical method, so there is an equation to solve. Welcome to another tutorial on flood routing concept. So today we will discuss about channel routing. As you know that flood routing can be divided into reservoir or storage routing, where the flood wave is coming inside a reservoir or a storage structure, And another type of routing is channel routing or canal routing or river routing, where the flood wave is coming from the upstream and going out through the downstream. So that is why what happens is, in case of reservoir routing or storage routing, which is also known as level pool routing, the storage is a function of outflow only, because whatever has come inside, it has created the storage. If you pour some water in a bowl, then that water will increase the water stored in that bowl. But if you create a hole in the bowl, then the water will come out of the hole as an outflow. And how much outflow will come, it will depend solely on the storage. Right? Suppose you have cut down inflow, but storage is already there. Now suddenly you have opened the gate of the reservoir. Whatever amount of water is there, it will tries to come out. If you do not close the gate, it will continually comes out. The water will continually come out of the reservoir. So that is why in case of reservoir or storage routing, the storage is a function of outflow. Okay, so storage is the function of outflow only. In case of reservoir or storage routing. However, if you consider about the channel routing, then channel routing is a function of both inflow and outflow. So channel routing is a function of both inflow and outflow. Why? Because whatever amount of water is coming inside a open channel, that amount of water minus the evaporation and infiltration or conveyance loss, to be precise, the remaining amount of water will only contribute to the outflow. And this difference between inflow and outflow will create the storage. Okay. So channel routing is a function, or the channel storage is a function of both inflow and outflow. And reservoir routing is a function, or reservoir storage is a function of only outflow. Keep this in mind. Now channel routing can be further subdivided into hydrologic routing and hydraulic routing. Now, in case of hydrologic routing, what happens? There are two different types of hydrologic routing can be observed. One is prism, one is wedge. So let us say that this is the cross section of the channel, and water is AB. This AB is indicating the width of the river channel. For both the cases, this AB is indicating the width of the river channel, and this arrow is showing the, what I will say, this arrow is showing the direction of the outflow. Correct? This channel, this arrow is actually showing the direction of the outflow for both these cases. Now, if you imagine a parallel plane or a plane parallel to the channel bottom, so anything above this imaginary plane is known as wedge storage, and anything below this plane which do not changes with the change in distance or depth is indicated as prism storage. Now it may happen that you see this one, what I will say, let me, yeah. So this one, this particular thing, this particular thing, you know, this one is your what do we say as the real water surface profile. This is the real water surface profile, and this dot line is the imaginary water surface, and this continuous line is your real water surface. So difference between these two surface area or surface level indicates the wedge storage, and anything below this dotted line you can say it as prism storage. Now it may happen that this real surface or water surface will goes below the imaginary water surface. So what will happen at that case? Anything below the imaginary water surface, anything means any water or any space or area below the imaginary water surface but above the real water surface is indicated as wedge storage, and it is indicated as negative wedge storage. That means anything above the imaginary water surface, or if the real water surface is above the imaginary water surface, then the difference between these two water surface level is indicated as positive wedge storage. And if the real water surface is below the imaginary water surface, then that difference of level is known as negative wedge storage. And the water which is below the imaginary water surface profile is known as prism storage. Okay, so this is what is known as the prism storage and wedge storage. Okay, so that is why it is written as when a flood is approaching through a channel, and if a plane is imagined parallel to the channel bottom, then the water which stays under the plane, that imaginary plane, is prism storage, and above the plane is wedge storage. Now what will happen is that if the depth of channel is assumed to be uniform, then prism storage is constant. If the depth of the channel along with the distance the channel has traversed is assumed to be uniform, then the prism storage is constant. However, wedge storage is dynamic. You see, however, wedge storage is dynamic and it will reduce from upstream to downstream, where the value will be positive in the upstream and negative in the downstream. Why so? Because in the upstream the flood wave has entered. Okay, so its peak is much more than the existing water level. So that is why it is above the imaginary water surface profile. So it is positive wedge storage. But when it is going to the downstream, due to the convective loss and also energy loss,